Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020. And this is the, when last we parted, you had this problem that you were working on. Again, we were forcing the system to experience resonance here. And I hope you had a chance to finish this, but if not, you have an opportunity now. So you know what to do. Let's see how you did. We need to know what K is. K is mg over L, and we substitute in. Note we're taking care of the units by moving those decimal points, and we get 75 for K. And we were told the system experiences resonance, and so the system frequency is the square root of K over M. And that's going to be the square root of, that's going to be 25, and that's going to be 5. And so that's why we put 10 times cosine of 5t there. And these are our initial conditions in the right units. So we set about solving this. What we'll find out is that our complementary solution will divide all the way through by that 3, and that is going to be d squared plus 25. And so we'll have c1 cosine 5t plus c2 sine 5t. And then we'll do our work with our particular solution. Again, this is going to give us another factor of d squared plus 25, so that is going to be squared, and that will give rise to t's. And what we're going to do is substitute into the original equation, do all of our undeterminate coefficients, but we will get this at the end of that. And so the particular solution is going to be 1/3 t sine 5t. Make sure you're getting these answers. Then we need to deal with the initial conditions, so we'll use those. This is not going to be a factor because our initial value is 0, so that's going to drop out. So what we will get is u of t is 1/5 cosine 5t minus 1/50 sine 5t plus 1/3 t sine 5t. And the last thing we're going to do is we will combine these terms into a single cosine term. Here we'll find the amplitude to be this, and here we will calculate what our phase shift is going to be. And we will get this, or it will be that plus pi. And so since the coefficient of the cosine is positive and the coefficient of the sine is negative, we're in quadrant 4. And so we know that this one is correct. So putting all that together, this is what we get. Notice here that this is 5t minus a minus, so that's why it is a plus. And so this is the sketch. Now you see that this t causes havoc because what will happen is this is getting bigger and bigger and bigger as t gets bigger. And so it is destructive vibration, and we call that resonance. Okay, let's look at the full problem now. So we're going to introduce damping to the equation. And the displacement function is going to be the complementary solution plus the particular solution associated with this right-hand side. Now, there are a couple things we should say from a terminology point of view. We remember from our work earlier about free damped cases that the complementary solution will approach 0 as t increases. It is going to be exponentials, but they're going to have a negative coefficient inside the exponential, so those will go to 0 over time. And since that goes to 0 over time, that is called a transient solution, or a transient part of the solution. And so that means that the behavior of the displacement will start to look more and more like the particular solution as t increases. So the particular solution is called the steady state solution, or forced response. It is the one that will endure over time. Okay, just so we don't have to do everything over again, let's take the system from the last example completely, but we'll add in a damper that will exert a force of 45 newtons when the velocity is 50 centimeters. Those are centimeters per second. Okay, and these are newtons, so you have to deal with the units. You know what to do? Let's see how you did. Okay, you have to get the damping factor, and it's going to be 90, and it turns out 90 is a very significant number. If you look back on some of the problems we did, this system is heavily damped. And we then go through and set up our equation. And we'll divide all the way through by 3. And we have this. Now, when we solve this will be auxiliary equation. We'll be using quadratic formula, and so we will get minus 15 plus or minus 10 root 2. And it turns out that that is negative each time as predicted. So this is our complementary solution, and that's going to be the thing that we call the transient solution. Now, when we look at this, then we're going to have the annihilator here is going to be d squared plus 25, and that's going to give rise to this kind of particular solution. We substitute that back into the original differential equation and set it equal to the right-hand side of that, and we work through that, and we'll get that the particular solution is 1 over 45 sine 5t. And so we have everything we need except for the coefficients here, and we'll use our initial conditions and substitute those in, and we will get this is our solution. And here is the graph. And notice that damping does happen, and in fact it was a significant damping factor, and no longer do we have a problem with this because things are very well behaved. So this is the transient solution causing things happening, but eventually it becomes the steady state solution. To be concluded, can you believe it? In 23.5. See you.